In today's video, we're going to talk about the phase difference and interference in one dimension. So by now, you should probably be familiar with the result of interference. You know that when the peak of one wave lines up perfectly with the peak of another, you get constructive interference, and when a peak lines up with the trough, you get destructive interference. So let's start by saying that what exactly is phase to have a better understanding of the interference. The easiest way to wrap your head around it is to connect the wave to a circle. Now, picture a circle, and I would separate it into four parts with a point at the edge of it that goes, for example, have a counterclockwise motion at steady speed. If you try to connect those spots and try to look at it at the vertical lines, you will get a sine wave. So, for example, let's first point our quarters. So here's 0 and 2 pi. Here, when we have 90 degrees, we have pi over 2, pi, 3 pi over 2, and 2 pi. So that's how we try to number our circle. A full circle is 380 degrees, and a tip around the circle, or 2 pi, equals one complete cycle of the wave. And now let's consider that point. For example, it goes counterclockwise, and if I want to follow its motion, I'll get something like this. It goes up, for example here, goes up, down, up, down. You will get a perfect sine wave. So that's how you can easily get the idea of a phase and what wave is. And basically, phase is that angle that it have with the center of the circle. For example, if our point is here at 45 degrees, our phase is just pi over 4. Or if it's at this point, you will get the 5 pi over 2 as your phase, or like, for example, if it's here, you will get that point as your phase. It just here, for example. It depends on where you get your point as the starting point, but usually you use it, for example, the positive x-axis as your respective one. So, for example, 45 degree is the phase is pi over 4 with respect to the positive x-axis. So now, imagine for interference, it's, as we talk, it's just a simple idea of sum of two waves. And in order to understand it, interference, we need to focus on the phase of two waves. So now, let's say that the phase part of a wave is written like this. V1 equals to kx1 minus omega t plus V0, V10. And for V2, kx2 minus omega t plus V, for example, 20. So the difference between the two waves, V1 and V2, are called phase difference, and we show it as delta phi. Oh my god. Delta phi equals to V2 over V1. So if we try to divide them by together, we get the kx2 minus omega t plus V2 minus kx2 minus omega t plus V10. If we try to simplify it, these would cancel each other out, and k is constant, so it would get out of the bracket, and it would be kx2 minus x1 plus V20 minus V10. So now, what is k? K is 2 pi over lambda. And notice that we can show this as delta x, and we can show this as delta phi. So the overall equation would be 2 pi times delta x over lambda, or like lambda plus delta v. So now that's the phase difference that that's a formula for the phase difference. And now let's get to the idea of what are they called? This called path. Oh my god. Path length difference. And this is called inherent phase difference. Notice that the formula for a sine wave is d, for example, a sine kx minus omega t plus v01. And if we try to add them up, before that, yeah, let me just explain this. So for example, d, the distance or displacement of the medium at medium, and for example this one is d1, and d2 is a sine kx2 minus omega t plus v20. So now these are the displacement equations of our two waves, where phases v1 and v2 were defined in the equation that we had right here. There's a trigonometric identity, and it's called it's like this: sine alpha plus sine beta is 2 cosine of alpha minus beta over 2 times sine alpha plus beta over 2, I guess, yes. So the identity is certainly not obvious. I mean, it's easy to be proven backward from the right side, but we can use this identity to write the net displacement of this equation. And if we try to do that, we get the equation of 2a cosine of delta v over 2 times sine kx minus omega t plus v average. So notice something here. This is a sinusoidal wave traveling. So what is x average? It's x2 plus x1 over 2. And what is v average? It's v1 plus, for example, v2 over 2. So if you consider this, like, where do we have the maximum constructive interference and the perfect destructive interference using this formula? So as we mentioned before, when do we have the perfect constructive interference, and when do we have the perfect destructive interference? When the crest of one wave matches with the crest of the other one, and when they are in phase, the phase difference and the phase difference is 0, they would get the perfect constructive interference. So now this part is for the amplitude. So we said when the phase difference is 0, we get the perfect constructive. Now let's put it here. Put out the formula. If you put 0 here, it's 2a. Code a is the amplitude of each wave, and a, when we draw like this, a, like capital A, it means that the overall a, like the sum of the two waves. So now if you put 0 here, it would be 2a cosine of 0. What is the cosine of 0? 1. And what is 2a? So the a, like capital A, would be 2a, which is which means that we have a perfect constructive interference. And how can we show it? Like, there should be a formula for it. Notice, when do we have the maximum amplitude? Like 2a cosine of delta phi over 2. Like, when do we have it? It's when, like, at this part, 0, 2 pi, 0, 2 pi, 2 pi, 4 pi, 6 pi, just, it's like 2 pi, 2 pi. It goes up by 2 pi. So the formula for the constructive maximum, or like, yeah, maximum constructive interference is delta phi equals to the m times 2 pi. And notice that, for example, if we again put 2 pi here, we get the idea of it. And then the maximum amplitude is a equals to 2a. For the perfect destructive, or like the minimum, yeah, let's call it perfect destructive. Destructive, perfect. We should just add it by half. So delta phi equals to m plus half times, oh my god, times 2 pi. And where m is like an integer. So that's basically what happens when we're talking about the phase difference and what is wave. So let's consider interference in one dimension. As we said, one of the most basic characteristics of wave is the ability of two waves to combine into a single wave whose displacement is given by the principle of the superposition. The pattern resulting from the superposition of two waves is often called interference. So now, imagine two speakers. This one is speaker 2, for example. And this one is speaker 1. They produce sound waves. For example, the speaker 1 sound wave is like this. And the speaker 2 produces sound wave like this. This is for speaker 2. Yeah, I should have drawn it like this, but yeah, something similar to that. And so, for example, the distance we want to point of detecting at this point. This one, the distance for this one is x1, and the distance for this one is x2, and that's it. So this one is two overlapped sound waves, and we can just try to look at it. And if you perfectly try to look at it, that what is it? Is it constructive or destructive? Yes, it's destructive interference. So now let's consider the two overlap light waves. So we have a laser, for example, here that produces a wave like this. And then we have a partially silvered mirror here, and then we have another laser over there. And that produces wave like this. I guess it should be, yes. Should be something similar to that. And notice that they're constructive, but they're not perfectly constructive. So we had the formula over here, 2 pi over times delta x over lambda plus delta v. Consider this one. So now we're going to, when the sources are out of phase, because they're not always in phase, and sometimes they can be out of phase. So now let's consider them. For example, I don't want to spend time drawing speakers, so I'm just going to copy and no, never mind. So for example, we have a speaker 2. Yeah, I'm just going to copy this one, which produces. So I've just drawn them to do not waste any time. So now let's just go over them and just try to talk about them. For this one, A, for example, in A, we have identical sources that are separated by half a wavelength. So when we say they are the identical sources, so the phase difference is 0. And then when we say, which is they are separated by half a wavelength, our delta x would be lambda. So now, let's, just to give you a clarification, don't confuse the phase difference of waves, which will be shown as delta phi, with a phase difference of the sources, which is shown as delta phi 0, like the one that we have here. It is delta phi of the waves, the phase difference of the waves, that governs the interference. It's not the difference of the sources, like the phase difference of the sources. So let me show you this. We have this one, this condition. So our formula for the delta phi is k x2 minus x1 times plus phi2 minus phi1. So now look at it. For the first one, A, to calculate the delta phi, delta k is 2 pi over lambda, right? Times our delta x is lambda plus our delta phi is 0. So in this case, the two waves are in phase with 2 pi, with delta phi equals to 2 pi rad and the interference constructively. Now, let's get to our second condition. Let's call it B. The sources are out of phase. And how can we draw that? Because, I mean, it's obvious that they're out of phase, but let's say that their delta x is 0 and delta phi is pi. So putting in the formula gives us 2 pi over lambda. The x is 0, so this one would be 0 plus pi. So this one give us something out of phase. So because it's pi, it's not follow up the formula of 2 pi plus half integer. So it just gives us a destructive one. So now for our third condition, for example, something like this. Our delta phi is 0. Delta phi 0 is pi half rad, half pi. And our delta x is 1/4 of the lambda. Just putting in the formula, delta phi equals to the 2 pi lambda times 1/4 of the lambda plus pi over 2 lambda plus our delta phi is pi over 2. We get 2 pi over 2, or again pi, which means that the sources are separated and they are partially out of phase. So that's how we can understand the interference in one dimension, and how the two sources, when the two sound sources are like combined together, how can we find the phase difference of the waves and phase difference. So we basically try to calculate the phase difference of the sources using the phase difference of the waves. So now let's try to do two examples. Pause the video and try to solve this problem. So it says two loudspeakers emit 500 Hz sound wave with an amplitude of 0.1 millimeters. Speaker 2 is 1 meter behind the speaker 1, and the phase difference between the speaker is 900 degrees. The speed of sound is 343 meters per second. What is the amplitude of the sound wave at 0.2 meters in front of the speaker 1? So again, it doesn't matter like what point it is. Their difference, their speed is same, same speaker with the same frequency and amplitude, so we basically have the same source. And here our delta phi for the phase difference of the sources, delta phi is pi over 2 radian. And notice something, we have the same amplitude and same frequency, so for the formula that we want, we need lambda, but we don't have that lambda here. It says that the speed of sound is 343 meters, and we have our frequency. So perfect, we need everything that we needed. So V speed equals to lambda times frequency. So when we want lambda, it's V over F. So our V is 343 meters over 500 hertz. If it give it, so the value would be, value would be 0.686 meters. So that's our lambda. So now we want to calculate our delta phi. The delta phi, the phase difference of the waves, I said it's different from the phase difference of the sources. This is the phase difference of our sources. The phase difference of our waves would be delta phi equals to, as we said, the formula x2 minus x1 plus phi2 minus phi1. What was k? It was 2 pi lambda delta x plus delta phi of sources. So what is the delta phi of our sources? Is pi over 2. What is lambda is 0.686. Delta x is 1. So we get the value of we get the value of 10.72 radians. So now we want to calculate our amplitude. When we go up here, this I said our amplitude is 2a, the amplitude of each wave, times cosine of delta phi of the phase difference of the waves over 2. So now for the formula for our amplitude would be 2 times, what is our wave amplitude? 0.1. 0.1 10 to the power of negative 3 times, what is the phase difference? 10.72 over 2a cosine of, I forgot to write down cosine. Cosine of 10.72 over 2. So we just need to calculate this, and the answer would be so the overall answer would be 0.127. If you like the video, please subscribe and like it. If you have any further question, you can comment it, and I would definitely answer that. Thank you for watching my video.